I'm going to bring back to the stage a man who obviously needs no introduction to the Cooper community, but some of you arrived this afternoon not seeing him this morning, so I do want to say this gentleman does have a published paper in Nature, as well as appearances on the History Channel, Discovery, Netflix, and HBO. And Tom Kaye is the most well-known scientist on the Cooper case. And the FBI is looking for a scientist outside of their labs to help with evidence and analysis, including the Cooper tie, the Tina-Bar money. Tom was selected, and he organized a team known as Citizen Sleuths. And you can find descriptions with photos of the testing that Tom has done at citizensleuths.com. So let's give a round of applause for the great Tom Kaye.
Thank you, John, for that wonderful introduction. And welcome everybody to another 2025 CooperCon. Yes, nice job. Under new management, looking really good here. Everything's run very smooth. Congrats to all you guys that made it happen, and a lot of work. So thank you very much. Looking forward to the next couple days. It's going to be great. It's going to be great. So today I'm going to talk about the tie particles, as usual. Last year I spent a bunch of time talking about the details of the instruments and how you read the data and that kind of stuff, and I was a little bit apologetic last year. You're not going to get any of that this year, so if you missed it last year, you should have been here. I will spend a couple of seconds pointing it out for the newcomers, but we're not going to go over a lot of that detail. I'm going to try and get through a lot of the things that have happened here in the last year. So I always start these things out with a request from all you guys. We work with McCrone Group, which is McCrone Laboratories out of Chicago. They are a world-famous laboratory. They charge premium dollar to do analytical stuff. And they've been working with us since the Josh Gates days, and they've done the first analysis, and they've done more subsequent analysis for us. And they have recently agreed to do 4 analyses for us for a fixed price, which you guys put up the money for, which we appreciate very much. And that's what part of this talk is about this year. It's based on the stubs we did over the summer. But in order for them to keep working with us, they have some requests. They want you to make sure, and tell your friends that talk about it, that McCrone does not do analysis, right? They do not interpret any of our data. They do not want to hear that somebody said, oh, McCrone said this. All right? They don't want to get anything pinned on them that made some claim, like we heard about Joe Weber. You know, McCrone said that Joe Weber's husband is not D.B. Cooper. That's the kind of thing that gets you in a lot of trouble. And that will instantly get us cut off from them. So, please, stay away from calling McCrone anything. Understand that we have a privileged position here. We had a privileged position with the FBI for a while, and when somebody started complaining about Larry, that got cut off. We're very sorry that Larry's not here because his mother is passing away, so we all have our thoughts and prayers are with Larry. Hopefully we'll see him next year. So we owe them a huge thanks. The news is that they might come next year. All right, I may have McCrone give a talk here next year, which would be great, wouldn't it? I'd love to see that. So I had him on the edge of coming this year. So what I want to do here is I want to get a little quickie video of you guys saying, "Please come," right? So what I want to do is we'll practice it once and then I'll videotape it. I want you to say, "Thank you, McCrone. Please come next year." So I need a lot of volume. I need a lot of enthusiasm, right? All right, so let me hear it. Thank you, McCrone. Come next year. All right, that was great. Better than I did. All right, let's try.
Get up. Get up.
All right, get up.
Stand up. Get up.
Thank you, McCrone. Please come next year. Perfect. Thank you so much. All right, that's going to really suss it for us, I'm sure. Okay, let's do a little preview here. So we rescanned 3 stubs over the summertime. We've scanned these stubs before, but we did it with a different instrument. They have a newer, more expensive, more deeper penetrating instrument. And we set it to higher performance settings. So whereas we only scanned each particle for about a second last time, we scanned it for equivalent of about 6 to 8 seconds this time. They have more detectors. We only had one detector before. Now they have 4 detectors looking at the particles simultaneously, so that for 1 second you get 4 seconds worth of data. So it really worked out great. The stubs we looked at were from the front of the tie. They were not from the knot. So the knot, if you remember from last year, had 180,000 particles on it, which was a phenomenal number of particles. These didn't have anywhere near that much. Still quite a few though, right? What we found on these stubs was that each stub was different, right? Not by a ton, but you'll see as we go through the talk, you'll see, oh yeah, that one's not quite the same as the previous one. Now, the problem that we've been having with all this data, and if any of you have looked at the Excel spreadsheets, which are available in Citizen Sleuth if you want to download them and look at them, is that each particle is in a row in an Excel spreadsheet. So you can imagine if you have 180,000 rows, and then elements are going out about 30 columns to the right, and it gives a percentage of what each element is in these particles. For you to look at this spreadsheet of numbers going both ways on this spreadsheet, it's a very difficult job to kind of say, well, is this important? And there are a lot of particles of this, or are these particles kind of the same, or are they different? Kind of grasping things in your head is very difficult. And that's what my group here has been working on for the last few years, is digging through these Excel files, trying to put together things that make sense. And you've seen this in the previous talks that we found, uranium and things like that. So in an attempt to get around this problem and be able to graphically look at all the particles at once in a way that we can all kind of comprehend and go, yeah, what's with that? And oh, that's kind of interesting. All right, we want to be able to do that in like a one-shot deal. Because if I showed you a bunch of numbers here, half of you would fall asleep. So I was looking for a way to do that. And the way we found to do that is by using a new algorithm. It's relatively new. It's like the last 10 years, which is new in the math world, right? Considering Newton was figuring stuff out, a couple hundred years ago. It's called the T-SNE, T-SNE. The abbreviation is T-SNE algorithm. And what this is going to allow us to do this year that's been different from last year is last year we were looking for the needles in the haystack. This year we're going to try and look at the haystacks themselves. So that's what's different. So what is this T-SNE thing? Well, this is T-distributed stochastic neighbor embedded algorithm. A nonlinear dimensional reduction algorithm that converts high-dimensional data, many variables per sample, into a 2 or 3D map while preserving local relationships. Points that were close to the original space stay close in the preparation. None of you here understand that. I don't understand that. There is one person here that does. It just happens to be Mark's wife over there. Thank you, Sarah. This is for you. So you don't need to know any of that, all right? But the idea behind this is if you have two particles that are kind of closely related in the elements that they have in them, it will cluster them together in a graphic relationship, which sounds pretty cool. It sounds like this is going to kind of solve our problem, right? So let's take a look at one. So this is a graphic. And in this graphic, you see there's a bunch of clusters. It doesn't seem to make much sense at the moment, but if you look and see, they're kind of color-coded here, right? So whenever you see a cluster by itself, and it's all pretty much one color, those are all related. The further apart they are from each other, the less related they are. But this process to get this graph from 50 or 70,000 particles that we find in a tie takes 2 to 3 hours on my fastest computer. So it takes a long time to process this data. And sometimes these graphs look all squirrely and I got to readjust the variables to get it to come out looking decent. So this took a considerable amount of effort over the summer to get stuff that looked reasonable. So if we look down here at the green, that's iron. Right? So everything you see there is iron-related particles. Now, what the original program didn't do that I had to add to the program was I said, well, depending on how similar they are, I want you to color code them and I want you to tone them. So you see it's very bright green down here and then it gets to be a dark green up here. What that means is the bright green stuff has a lot of iron in it and the darker green stuff has less iron in it. Now, why is it important for us to look at that? Because if it's a commercially made pure product, the odds are it's going to be the same color throughout that cluster. If it's more of a natural product, it's going to have all kinds of variability in it, and that variability will come out in the gradation of the color. If you look over here at titanium, it starts off red here, which is not 100% pure, but relatively pure compared to this end. Calcium, same thing. Up here, you've got a couple things in a cluster, but you have two different colors altogether. That's a little different situation. When you see a cluster, and it's got two colors, but they're still mixed together, that means, let's say there was iron and aluminum. Once the iron quantity got smaller than the aluminum quantity, it changes color. But they still cluster them together because it's iron and aluminum together. Does that make sense? All right, because this is the whole fundamental thing of looking at these graphs. Everything I'm going to show you today is based on this. Now, the one thing that doesn't follow through all the graphs, it's an anomaly of the program. You cannot assign green to iron all the time. The next graph I show you may have iron, it could be purple. So the color does not stay with all the stuff I'm showing you. So you have to look at the clusters, and then we'll look at the gradation of color in the clusters, but don't look for green in all of them. So, how is our data analyzed? So we identify an interesting cluster by looking at these clusters. And we can say, okay, that iron cluster had something particularly interesting, or let's say a calcium cluster looked like it was particularly pure. So what we will do then is we'll extract out the calcium parts of the Excel spreadsheet, and then we'll feed it into AI, and we'll do a deep research run on AI. And deep research takes 20 minutes to half an hour to run. It actually goes away and it comes back and it tells you when it's done. What we get back is like a 20 to 30 page report on everything it found about the particles. And what we usually ask AI, are these particles commercial, consumer, or are they natural? Because at the end of the day, we would really like to find a particle that is a commercial particle that is only found in like one or two places that will narrow everything down. Eric Euler's tried to do this with the titanium, or the antimony and titanium, and it would have been a great find, but it turned out the particle was not what we thought it was. So once we get the multi-page PDF, we can then analyze it to see what's going on. If we find something interesting and it makes sense, we can then go back to the electron microscope and we can relocate the particles of interest and then analyze them at a deeper depth. And that gives us a whole new level to look at. And sometimes those levels can be quite different than what we saw. McCrone does not do a very deep analysis. He gets the top 2 or 3 or 4 elements. It does not get every possible element that is in those particles. So even if it says maybe this is 100% pure, whatever it is, once we go in and re-examine the particle, it may only be 70% pure, and there's a lot of other things that McCrone just couldn't see with the amount of time we had on the machine. So let's take a look at the first stub, which is the one from last year. It's the 6751. This came from the tie knot. This was the 180,000 particles, and it's the same one that I just showed you before. Now we're going to go into some of these clusters and some of the other ones. So we're only going to talk about this particular zone here. This zone here, you see it's pretty much one color, but it's broken up into multiple clusters. In some of the other stubs you'll see this same zone is going to be broken into a few different colors. But what we have here is very similar particles, but they're different enough that it clustered them into different areas. Now, back in the early days, 2009 or 10, we would see these particles, but we would just call them sand and stuff. Today, we understand that these are clay particles. Now, clay, in terms of geology, has a very different meaning than the clay that you used to make little farm animals with when you were young. Clay, in this context, is the kind of dirt that gets on your shoes and gums up your shoes while you're walking through mud, and when you get it in your clothes, it doesn't want to come out. It results from the wearing out of solid rocks into microscopically small particles. and these particles have different characteristics. So clays are actually mined, and the mining happens with these different minerals. Many of you have probably heard of feldspar. Kaolinite and zeolite are other ones. So each of these will produce a clay, kind of generically speaking, but each of them will have a slightly different composition. Now these are aluminosilicates. Oh, did I say that in the last one? Yeah. The main components are aluminum and silicon in these. And the aluminum-silicon ratios are what vary, and that's what separates them out into the different clusters that you saw in the deal. The predominance of particles, I think it was 80,000 particles on this stub, were clay particles. That's a lot of particles, and we've been ignoring them for a long time now. So finally we said, well, let's take a look at these and see what we have in these clays. And this is actually the basis, it's one of the main points we make in the scientific paper that we're putting in to get published right now, and I'm co-authoring with McCrone on this. And we make a point that for the first time an automated analysis has been used to examine 80,000 particles, and we use the clustering of these particles to come up with something that we can say about where the minerals came from. So where do these minerals come from? They actually come from fairly localized zones around the country. So you're not likely to find this clay in Illinois. You are likely to find it over on the West Coast or down in Texas, and each of the color zones is color-coded. Some of them are overlapping, as you can see. Now, is it going to pinpoint them down to some city? No. But this is another tool at our disposal, and it's an interesting characteristic that's come out of our research. And it may provide an actual basis and foundation for others to do this type of work, and we may solve other problems in other forensic cases. So it'll be good to know that maybe once we're all done, we're not meeting here anymore, that this will live on after us and potentially be useful, as the diatoms will be in other forensic cases. So in our paper, we actually show this graphic. So on this graphic, each of these lines represents the percentage. So if we come right here, this means it's 60% silicon and 20% aluminum. So if you've got a 60-20 ratio, you're on the feldspar line. If you're here on kaolinite, if you go right here, we're at 40-40. So we're about 50-50. 50-50. Does that make sense? When we're 50-50 aluminum, silicon, you're on this line and you come from this zone, this type of clay. If you're in the 60-40 line, this is it. So if you notice, this is a heat map. When we analyze all the particles, we've got a hot spot here, we've got a hot spot here. Ignore this. This is where everything clusters together and always turns red no matter what you do. There might be something going on here. It's a little bit off, so maybe it's a mixture of a couple. But we've got a couple of hot zones to look at. So again, if we come up with an interesting, something interesting on a suspect, then maybe this can help us out. But it's an interesting scientific process that we're going through on this. We're also going to take a look here at the magnesium cluster. This cluster showed up on this stub, and it really didn't on any others. The problem with this is very pure. This is, as you see it, the color is very consistent, and I think it's in the 80% magnesium range on this. Now, when we put through the AI, what we found out is that natural magnesium particles are about 30% real magnesium, 30 to 40, and then everything else is, extra garbage in the sand. So this is not a natural product. This is some type of commercial product. Do we know where yet? No, but it's another quiver. You can also see that the ratio changes when it goes from purple to blue here, so you know that the ratio inverts there. Another thing we found on one particular particle here was a crazy number of elements. This is a lot of elements to find in one teeny tiny particle, smaller than a blood cell. And there's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 different elements in this particle. Stuff doesn't come with 13 elements in it. Things don't happen like that. So this is obviously not a natural particle. The thing about this particle and the story that it says is that these elements all had to be in one place, and Cooper had to touch them and then grab his tie and stick them on the tie. So all these elements had to be stacked up in one place. This is really hard to do. And this is not the craziest example. I'm going to show you another example further in the talk. So these were some of the interesting things that came out of the cluster diagram from last year's stub. So let's move on to one of the new stubs. And this is from this year now. So this is 667. This is from the front of the tie. There's about 30,000 particles. And now you can see that this cluster diagram has some very different looking characteristics. If we look here at the clays, you can see the clays are kind of a mess here, which we expect because we know there's a whole bunch of them. This one's weird though. Right? You can say like, all right, why is the cluster forming like that? I mean, it immediately comes out and sticks out in your mind. This is what we were trying to do with this algorithm. We were trying to create something that says, that doesn't look right to me, all right? So what is that? It turns out that that's a gold cluster. That's a gold cluster. So why is it separating the two gold clusters into two stacks like this? Well, this side is gold and palladium, and this side, strangely, is gold and lead. So there's gold and lead together on that side, and that's why they're separated out. And then there's a continuous percentage. You see it comes down to here, and the percentages change. And then this is where it inverts here. So the palladium thing, and I pointed this out last year, and it's also in our paper, that one of the weird things that we find is that there's a gold-palladium mix that goes from 90% gold, 10% palladium, to 90% palladium, 10% gold. This makes no sense. This makes no sense. If you come up with somebody that could possibly have weird combinations of gold and palladium, he's going to be Cooper, right? Because I don't think you're going to find this in too many places. All right, this would be a key thing to look for. So this was kind of crazy. And there's 5,000 particles here. Last year, we looked at the uranium. There was one particle. I did spend a lot of time trying to find another uranium particle. Actually, I spent too much time on it. Could not find another uranium particle. So, and we just that's a dead end at this point. The problem with one uranium particle is that it could be there by chance. 5,000 particles, not there by chance. Not there by chance. So this is kind of a cool find. The other thing we can do is look at tiny clusters. So this is a very small little cluster, right? So these little small clusters take the more exotic things and stick them over in their own little corner. And in this case, these red dots were fluorine. Now, fluorine is not something that's common. Most of you have probably never heard of fluorine. It is an element. It's normally a gas. So when you see it here on this thing saying there's a particle of this stuff and it should be a gas, it makes no sense. But something you have heard of and does make sense is this is what Teflon is made out of. And you've all heard of Teflon. So I thought, okay, cool. It's a Teflon particle, right? It's a Teflon particle. I go, did they have Teflon in the 60s? I actually kind of got revved up about this. I figured, man, if he's in the R&D department and he's figuring out Teflon, Cooper vortex again. Teflon was being used in all kinds of pots and pans by the late 60s. So that didn't help, right? I wasn't going to get it. But then there's another twist, right? Because Cooper never leaves you hanging. He always wants to confound you some more. So I went in and I looked at the particle. I'm expecting to see something like a chip of fluorine off of a pan, piece of plastic, something solid. This is a smear. Now this was unexpected. This is a smear. And there's some little bright white dots in here. Okay, now what am I looking at, all right? This is getting vortexy again. Okay, what's this made of? So I zoomed in and I took a spectrum, and this is, if you weren't here last year, each of these little peaks represents an element. That's an element. That's an element of fluorine. And when I zoomed in, I took a spectrum of it, and it turns out to be pretty pure fluorine. That is, it's not a gas. So obviously there's something else attached to it. It's probably carbon is attached to it, because this is fluorocarbons. You've heard about them killing the atmosphere and all of that, right? Fluorocarbons. We're sitting on a carbon sticky tape, so we can't measure carbon. But probably this is fluorine and carbon mixed together. The thing is that it's still a squishy liquid. What kind of liquid is a fluorocarbon? It would be fairly exotic to have that in your laboratory or something. It's not something you're going to find in anybody's home, right? A fluorocarbon like that. But then it got weirder. They said, well, what are the white dots? If the white dots are not the fluorine is everywhere, and I mapped it to determine that. This is where all the fluorine is. It's everywhere. When I zoomed in and I looked at the dots showed up with molybdenum and calcium here. Calcium and magnesium. So this is like magnesium fluoride and calcium fluoride, which are two other components that accept fluorine. So we've got 3 different fluorine elements in this little tiny cluster that doesn't even consist, I don't think, of more than a dozen particles. The particles that did show up were multiple hits on this same smear. So as the thing goes back and forth, it can sample the same thing multiple times as it goes back and forth looking for particles. So very weird. Fluorine. It's another one that wasn't on our list until now. So suddenly fluorine is showing up as part of the Cooper world. All right? Another one to keep your eye out for. So let's move on to Stub 665, 47,000 particles. Another one from the front of the tie. And we look at the T-SNE diagram for this one. And this one's a little different too. Over here we have our clays. Again, you can see, you kind of get the idea now that there's a bunch of them. They have varying characteristics happening. This is titanium, I'm pretty sure. And this is calcium. So what do we see out here? We didn't see this in the other clusters. What is that white line out there? And we've got a similar looking line down here. So let's take a look at that. So this is calcium. It's calcium. And what I'm going to do, if this works correctly here, is I'm going to show you something very cool. I'm popping into a browser here. Hopefully I'll be able to zoom in. I'm going to show you what we can do with a cursor on this stuff. Now, this is another cool feature that I added to this program. You see, as my cursor goes over this, it tells me, can you read it okay? Oh, it's not showing up. Oh boy. What I see is different from what you see. Alright, it's not showing the screen. I misfired. Alright, I'll have to talk you through it. So, what you didn't see that I just saw is if I put my cursor on this HTML page that is developed, for each dot it comes up with what are the major elements in that. And if you look on this line, it's all 100% calcium. 100% calcium. And the rest of this you see is all green, and this is all very pure calcium. That's not natural. So we put it into AI, and AI came back with that this is a processed, very pure limestone, or lye. Lye is another term for it. Well, what is it typically used for? It's used for several things, but the one thing that kind of fits into the picture that we have so far with Cooper is it's used as a flux in making metals. So when you melt metals, they've got contaminants in there, and you put this flux in with the molten metal, and it sucks the contaminants out, and then you scrape this off the top. Maybe if you've ever seen somebody pouring zinc or aluminum or something, they scrape a bunch of crap off the top, they throw it away. That's what this is used for. So this points to some type of a metalworking deal that used very, very pure limestone. It's like 98 to 99% purity. If you go to this end of the cluster over here, it's like 97, 98% pure. So that was different. This is a nickel cluster. I'm showing you this just to give you an example because this is not interesting. As I've said in other talks, we have nickel wires running underneath the carbon stubs that all the particles are sticking to. So we see nickel all the time as a byproduct. But this again reinforces the idea. This is all the exact same color. The nickel's all the exact same material. So if we find a commercially made pure material, this is what it looked like. We've got a couple outliers here. I don't know what those are. But let's go take a look at copper. And this is the first of two that I'm going to show you. But I'm showing you two because we know it's more than just a one-shot wonder. What's interesting about this is copper has this copper zone with these little particles in it have four different versions of copper. One is pure copper, another one is zinc with copper, another one is tin with copper, and another one is nickel with copper. So, pure copper is used in electronics. You can imagine every circuit board has got pure copper on it. Zinc and copper is the brass for pennies and bullet casings. So can we stick them with a gun at this point? Probably not, because you could rub something off a penny, but it would be pretty unusual. But besides that, we also have tin and copper, which is known as cast bronze or red brass. So he was involved with brass and stuff that makes bullets and pennies. But there's a third one, the nickel alloy is nickel and copper. And that's the same thing that you see on a nickel coin. A 5-cent coin is made of this alloy. And industrial hardware is made from this alloy. So we have four different versions of copper in one tie spot, 1/2-inch spot. It's weird. I mean, you guys don't have these four. I have a machine shop, and I don't have all these versions of copper, of alloys of copper in my machine shop. So this guy, as usual, really, really gets around. And we'll look at another one a little later. This was one of the most interesting things that we found. This is a titanium dioxide cluster. The upper zone here, the upper cluster, is titanium and chlorine. The bottom cluster along the bottom here is titanium and silicon. So there's two completely different combinations. Now, chlorine doesn't want to come with titanium. You don't go dig up titanium and find chlorine with it. It doesn't happen that way. That is industrially processed titanium. However, the titanium and silicon is more of a natural process. And this is something that I just discovered from doing this research, that titanium comes out of a sand. There's a particular sand that titanium is made out of. It's called rutile. And it has to go through multiple processing steps in order to get high enough purity to make it go into making titanium metal. And I didn't understand this before, that there's multiple steps. So what we're seeing in the bottom cluster is an early step, and what we're seeing here is a later step. So if you just went by this cluster and these particles, you would say, okay, Cooper is in a titanium pre-processing thing, getting ready to make titanium dioxide, getting ready to make titanium metal. It's pre-processing this stuff. Okay, so this is interesting. We go under the SEM. And I'm quite surprised to find there is a ton of this stuff. And it's smeared onto the tie. A lot of it. But if you notice, it's looking a little granular down here. Doesn't it look a little granular? So it's not like it's pieces of metal. It's got some kind of fine granular thing. So I zoomed in. Now look at the magnification. This is 24,000 power. 24,000. That's a lot of power even for an electron microscope. And you see, these are all titanium dioxide, which means it's titanium and oxygen, which is very typical. And they're all little balls. And they're all very consistent. So I go, well, is this titanium sponge? Because titanium sponge is what they used as a precursor to make titanium metal. We have some RMI titanium sponge from the 70s in my sample box. So I pulled that out. And I looked at the titanium sponge. It doesn't look anything like this stuff. Nothing like this stuff. Now, what's crazier is the size difference. This is titanium sponge normal. You see this little picture down here? That is those little balls at the same scale. So you see how much smaller all these things are. So we put that into AI, and it came up with a couple things. It could be that they're processed titanium dioxide. They make them into very small balls to make very white pigment for paints and things like that. Could be that, but we couldn't validate it. Went in and zoomed in further. This is 47,000 power. And what we wanted to know was, how big are these little balls? Well, these balls are about 150 to 200 nanometers. This is one of the smallest things we've ever measured on Cooper's tie. At 200 nanometers is really small. And the only thing we found on the web was this picture that looks an awful lot like it. And these balls are about 150 to 200 nanometers in diameter. So this is something else that we can look into now, this titanium dioxide pre-processing. If somebody comes up with a process that specifically produces these types of small, teeny little balls, send me an email, let me know about it, because it's pretty interesting, Let's move on to Stub 566, 70,000 particles. Again, another group here. This is calcium down here, different colors, got that same kind of line on it. I don't know I think this is titanium. Again, we've got the clays going on out here. This is the nickel out this way. So let's get into a couple of these. So this is the calcium cluster. It's basically the same as the other one. It's high purity limestone used in steel and metal refining. But there's a lot of particles. And now we know that the particles are very similar, and they're in two different spots on the tie. So the tie is probably loaded with this stuff. Right? This was not a one-day hit. This is probably somewhere he spent a lot of time. Let's go look at the titanium cluster again. This one, as usual, it's got something strange about it. This one's missing all the chlorine. There's no chlorine in these guys. It has 30% oxygen, but some of these are very high percentage. Most of them have silicon, calcium, and aluminum, which means they're more of a natural product. So they're probably further upstream in this whole process. So in the lower corner here, we drop down to only 40% titanium. So it does run into some other mixes. So we think this is potentially either slightly pre-processed or some natural material. Take a look at the iron cluster here. This is again an example where you see a gradation, as I talked about before, going from bright green to darker green. This is a natural mix. We think this is a natural mix, probably rust. So rust turns into tiny iron particles. You get them everywhere, so we can't pay much attention to it. These little guys down here, that's nickel and chrome mixed in with the iron, and that's a cutting tool. And we've seen this before, so we know he was involved in some kind of machinery that was cutting metallurgy. That's typically what you use this stuff for. Not very much of it. If anything, he spent a very small amount of time in the machine shop. He wasn't drilling holes all day. He wasn't involved with people that were manufacturing machine parts. This is the second copper cluster. And this one has a better separation of the different types. Fewer particles in this one, so you can see there's 3 clusters. So again, all of the same things that were present in the past one are present in this one. And it's the pure copper that doesn't come along easily, along with, you don't generally machine pure copper. You machine a zinc alloy, a tin alloy, or a nickel alloy. You can machine those into things. You typically don't use pure copper for too much. You would use an alloy. It has much better characteristics. When we went and zoomed in some of these things, we found something weird. Because if you don't find anything weird, it's not Cooper today. We found molybdenum and chlorine. No idea. No idea where that comes from, right? No idea why molybdenum would be in there. I think it's the first time we've seen molybdenum. Again, it's checking another box on the periodic table that Cooper really gets around his elements. So, crazy. We don't know. Small amount. Could it be a dust ball? Maybe. We didn't take a deep dive into it. But it's interesting. If you find anything that has copper and molybdenum, let me know. Again, we look at the clay cluster, same thing. Very similar to everything else. different grouping. We talked about that, but I wanted to show you the examples in each one of these stubs. We can go in and look at some of these smaller clusters. These are the isolated ones that are rarer and sometimes more interesting. We were trying to look for these in the past years to find something interesting. This is zirconium and aluminum, 200 pieces. One is analyzed out as foundry sand, which we talked about last year. The other is aluminum zircon alloy, which is used as an additive. So this again, it points to metallurgy, even these small quantities. Everything we see here is pointing to metallurgy. We have this small cluster here, cerium and lanthanum, which we know about because it comes from lighters. When you click that lighter and that flint, that's what this stuff comes from. We've seen it before, but I'm showing you how these clusters can be identified. If you want to look at these clusters, I can easily send you the data. So we're going to wrap up with the strangest particle that I think any of us have ever seen that are working on this project, and it's been like 15 years now. Looked at this thing, and when we did spectrum on it, came out with 20 different elements. Each of these peaks is a different element. Here's the listing on the side. Now, we've got Yanks, who is our metallurgist that works with us. He's a very professional guy, knows his stuff. We sent him this, and we said, what do you think? And he gave us a one-word answer, which I was disappointed at. He said, wild. That's all he said, right, Nikki? He said wild. Yeah. So, if Yanks doesn't know what it is or how it got there, I'm not even going to hazard a guess. But this, again, all had to be in one place for him to get one, even if it's a dust ball. I know it's a dust ball because we actually did a map of it. So it's not one chunk that's got all this stuff tightly packed together. It is a dust ball. It's kind of expected. But the problem is, who in the hell has got dust sitting in the corner of their machine shop or metal foundry or wherever the hell he is that's got this many elements in it and ends up on your tie? Stand by. Technical difficulties. Yeah, so how this many elements gets on the tie is completely perplexing. And this is one of the things that came out of this year's research is that, the deeper we dive into this, the stranger this whole Cooper thing gets. So, our work is kind of cut out for us. So to summarize, our cluster diagrams show pure versus natural particles. And it's been very good at doing that.
Hey Tom, you popped out full screen here this year.
I can't even see that. Is it good? No. I can't see that on my screen here. Hold on, let me see if I can. There you go. Okay. The copper and gold stuff had multiple sources. Unless he was mixing platinum and gold together in some shop somewhere. We also saw large quantities of commercial elements here, which is kind of nice. It's kind of nice to know that. We had no way of really determining that before. We would look at a few particles, and we could, hazard a guess. But when you see hundreds of thousands of particles, and they're all extremely similar, we know that's probably a commercial source. The clay particles remain as an interesting sideline in this whole thing. We're working through that. We'll see once this paper comes out. If somebody comes back as an expert on aluminosilicates and says, hey, did you think about this or do that? Maybe it's going to lead us in some new direction, but we're throwing it out there to the scientific wind to see what's going to happen. The titanium balls, I personally think, are the most interesting because they're hard to put together. They're hard to make 150 nanometer consistent balls out of anything. And that's something worth looking further into, which will probably happen over the next year. But we encourage you, again, this is not just me, this is all of you looking into this to make it happen. Molybdenum is the new element. It's this year's uranium, it's this molybdenum thing. We can't find a ton of it on the tie. It is there. It's a confirmed hit. So to conclude, to date we've analyzed 438,000 particles. We've written more than 30 custom Python programs in order to do this analysis. All the roads lead to some sort of specialty metals thing in a filthy environment. And he probably worked at different places, because I can't imagine any one place having this many different things in a place where you could get it on your tie. And we know he only had this tie for a maximum about 6 years from when it was being sold to when he jumped off the plane. So this tie in the 5 or 6 years got around to a lot of places. So if we do find a hot suspect, and he does turn out he had 5 different jobs in 6 years, that'd be pretty good, especially if it was in the metal industry. What's happening now that we've done this many particles is that the new information is falling off at this point. You know, at some point, every new particle is telling you something new. At this point, we're kind of plateauing, and we're not getting a lot out of the next 50,000, 100,000 particles. So we've got to think about doing something different. So to kind of recap, this is where it started back in 2009. We found this titanium shard on the tie clip. It was one of the first particles that we found. And this is made of pure titanium. It has low oxygen. It is titanium metal for sure. And this is what got the whole particle analysis and driving it for 15 years now, moving forward. So we thought, well, if this weird thing is on the tie, if we can find some more stuff, then we can locate it. Well, there's a lot of weird things on the tie. They're so weird that we're having a hard time narrowing them down. And if we go back to the early days here, I guess in 2010, 2011, this is the original particle tree that I showed very early on, one of the early Cooper ponds. And this has a lot of the same stuff we're seeing today: titanium, salt, chlorine, aluminum, gold, silver, clays, calcium, and iron. So this family tree has gotten bushier, but it hasn't changed substantially. So where do we go from here? We want to continue to work with McCrone. And that is a big, big plus for us. And they are willing to work with us. They would like some good publicity out of this thing. Because I went to McCrone, I got the tour over the summer, and the president came out of a meeting to meet with me. That's a good sign. And he said, we really like working on this project because we don't do many things that get us good publicity. Now, the working word there is good publicity. All right? So if we don't screw that up, if we can get some nice play out of this, and we've gotten play out of it, it's really going to help us. And even having you guys all know the McCrone name and that little video that I'm going to show, and I'm sure the president is going to see, all right, that's a whole boost. That's a whole boost. So we have one more stub left to analyze. It's the other side of the tie knot. We have one shot left. You guys put up $2,000, and that was going to get us 4 shots at McCrone. We've used 3 of them. We have 1 shot left, 1 bullet left in the chamber. They've not charged us yet. Okay? They've not charged us yet. Will they charge us? I don't know. Right? Maybe if they get a nice play on some newscasts, probably not. Somebody calls up and complains, probably getting a big bill the next day. Okay? Just a warning to everybody. I got the tour and I saw all the instruments they had. And of course, I'm looking at all the instruments, so I want to know what else can we use in this playground, right? This is a huge playground. There's, I don't know, $100 million worth of instruments in this place. Beautiful, beautiful facility. He has this thing called a SIMS instrument, S-I-M-S. And I don't know much about it, but the way he described it to me, I think you'll relate to. He says, when we want to demonstrate this machine, we take a dollar bill out of our customer's wallet, and we stick it under this machine, and in like 10 seconds, it tells us that there was cocaine on the dollar bill. Right? Now you all know, how many years cocaine and dollar bills has been a ubiquitous thing. It's on every dollar bill. But it can detect it that fast. It does something with helium, ionized helium, blows helium over the thing, and it sucks up stuff, and it goes into the analysis. So what's interesting is we still have filters from when we vacuumed the tie. Remember back previous days, Eric Eulis got one of our filters and tried to have DNA analyzed on it, and it was a sad ending to a documentary where it didn't match his suspect. Well, what they didn't tell you is that the DNA matched me. So it was my DNA on the tie. So we have more of these filters. So what I'm hoping we can do is take some of these filters down there and have them blast this with the SIMS machine. And what we'll be doing this time is we've looked at elements all this time. This has always been about the elements. It's never been about how you put elements together to make a molecule. Well, this SIMS thing can measure the molecule because cocaine is a molecule. So I don't know, right? I don't know whether we're going to see this in there, but we're going to be talking about some of this future stuff on Sunday, so I'll kind of leave it there. The data availability on this, I want to make sure that everybody knows I'm not holding this data back. I'm not going to probably stick it on the web for now, but if you want it, let me know specifically what you're interested in, and I'll send it to you. The Excel spreadsheets are pretty easy. The HTML files are also pretty easy, but I don't want to lump them all together and just ship them out to people who are not going to use them. If you've got a serious interest, let me know, and I'll send you what you need. All right? So I'm not going to hold back on that. And in wrapping up, I'd like to acknowledge all these people that helped on this. A lot of them are here. Thank you guys for all your help. Sorry Larry Carr is not here. And for all you guys that funded this research. So you're all part of this project. So thank you very much.
Thank you, Tom. We're going to spend a long area. We know there's a lot of people who would like to taste some beer very soon, but we do want to spend just a couple minutes having Tom answer some questions. Anybody have a question for Tom before we wrap up today? That wasn't the pressure.
Did I really explain it that good?
Yeah. Yes, over here.
So it sounds like that, it's had a very big chain of custody since hijacking, but it sounds like what you're finding can conclusively be attributed to the owner of the tie at the time of hijacking. Is that a fair conclusion?
No. The question is, can we attribute the tie to Cooper, the hijacker? No, we're at a Y in the road now. Right? We're definitely at a Y in the road. If you're going to go with the particles, we go this way, and Cooper owned this tie and was part of this. If you're going to go with the idea that this tie came from a resale shop that Cooper shopped at an hour before he went on the plane, then you're wildly open to whoever suspect you want. Your suspect, if you're following my path here with the particles, has got to have a plethora of these particles in his work environment. So we are certainly not on either of those two roads at the moment. Does that answer your question? Okay.
Tom, part of my ignorance on this, but I know Eric was working on trying to look at amalgams like titanium and antimony in certain percentages that got tied back to a particular patent that then can be tied back to the owner of the patent, the company. Is any of this new research allowing you to find similar patented combinations of elements?
We would certainly love to see that. The holy grail here is to find something that is a true alloy, and it's got two things that don't go together naturally. And it tracks back to some research thing that wasn't happening in a big way in the 60s. And we have not found that particle yet. Eric had the right idea. Eric had the right idea back then looking for that type of particle. The problem was he didn't wait for me to go in and take a deep dive and analyze that particle. That particle happened to be two particles put together that got analyzed together. And they just happened to come out with the right percentages. So this is very tricky stuff. This is very tricky stuff. This is why we don't spend, forensics doesn't spend a lot of time doing this. You can spend we spend a lot of time on this, and you can come out with kind of a null result in the end. I don't think we're at a null result. I think we've got Cooper narrowed down to a very small area, if you believe in the tie particles road. So I think that's what you look for. You look for them in that specialty metals area.
Sharon?
What is the rarest particle element in the top. Can you narrow down like where he would have worked within just based on one?
Yeah. So what's the rarest element on the tie? That's probably a tough thing to classify, right? Because off the top of my head, I would say the uranium is pretty rare. Because we only found like 2 particles of uranium. So,
But like in the country.
but is it rare? But is it rare in the natural world? No.
Right.
No. You can get 1 particle of titanium on any tie in the joint here.
In the natural world that's on the top.
Oh, what's the question? I'm sorry.
Yes, what's the rarest element in the natural world that happens to be on
It
the top?
happens. I don't have a clean answer for that. That's an AI question thing, and that's a good question to ask. I don't know what the rarest one is. I know that you're saying what comes out of the ground the least. Well, there's rare earth elements.
Like that's where he was. And then
Well, you can't say that's where he was. There's so many places. Well, the rarest elements. Rare earth elements, which are called rare earth elements, are not actually rare. They're just spread out so thin that you can't find them. There are rare earth elements on the tie. Is that rare? I don't know. I would say offhand uranium would probably be the thing, but I'd have to look and see. I don't know how prevalent antimony is. I don't know how prevalent some of these other ones are. We've covered most of the periodic table now. There has to be one winner in there, but that's a good question. I may have to dig into that a little bit, or you can do it and call me up and tell me you made a discovery. I'll have to give you credit next year.
I like that.
Does that answer your question?
I like that.
Okay.
All right, Tom, thank you. We are going to go look for particles in bars and pots and things like that.
Good idea.
43